Okay, let's start our day 4.
Okay. Um, so hello everyone, and welcome to the fourth day of the QBronze entangling workshop. So today we're going to be going over entanglements and a couple of protocols. So before we jump into the content for today, as usual, I'll just do a brief recap on a couple of things we covered yesterday. So today we'll be looking at entanglement, superdense coding, quantum teleportation, and a few other notebooks. So I'll just start off with the recap. So yesterday we started off by talking of operations we can apply to a single qubit to change its state. And we introduced the RY operator. So we have a general form for a qubit where just by changing the angle here, we can get a different quantum state. So we said with the RY operator, we will have a quantum state. And when we apply the RY operator or the RY gate, we can perform some rotation and end up at a new location, which will be a different quantum state. So we have a circuit here to try this out. And our circuit consists of 1 qubit, 1 classical bit, 1 qubit and 1 classical bit. So if you introduce them to our circuits and we've specified the angle we want to rotate by. So when we want to perform the RY rotation, we specify the angle we want to rotate by, then we multiply it by 2. And we also specify the qubits that we want to perform the rotation on. So the rotation angle that we're specifying here is the rotation angle on the unit circle. And we're multiplying by 2 because we want to get an angle on the Bloch sphere. So we're not going to go over the Bloch sphere in this workshop. But if you end up participating in Q-Silver or any other quantum computing workshop, the angle that we're rotating by, not the rotation angle. So when we multiply the rotation angle by 2, we get an angle on the Bloch sphere or the angle on the Bloch sphere. So finally, when we've specified all our parameters here, we can finally measure and retrieve results. So the angle that we rotated by here is 2 pi over 3 or 120 degrees. And these are the results we get. Okay, so this is the operator for rotation. And by specifying the angle theta here, we can specify an angle we want to rotate by. So for example, let's say we had our quantum state initially here. So let's say our quantum state was initially the 0 state. if we perform a rotation and theta is, we perform a rotation using this operator and we set theta to pi/4. So we're going to rotate from the state 0 to the plus state. And we can even perform multiple rotations. So here, we have an example whereby we keep applying the rotation operator. So we started off here, we applied it once, twice, 3 times, 4, 5, 6, 7. And on the 8th, when we applied it the 8th time, we ended up back where we started. Okay, then we moved on to reflections. So on the unit circle, okay, so we introduced an operator here, the Z operator, and we tried applying it to a quantum state here. A quantum state that we are visualizing on the unit circle. So when we tried applying the Z operator to our state U, we ended up on U prime here. And when we applied it once more, we ended up back at U. So we said if this was meant to be a rotation operator, we would have rotated by this angle first, then we would have rotated by this angle next to be alternating between these two states, which doesn't make sense because when we rotate, the angle we rotate by is consistent. So on the unit circle, the Z operator is not a rotation operator. So that's where we started off. That's where we started describing reflection. So for reflection, we need a line of reflection. In this case, our line of reflection will be the x-axis. So when we've stated our line of reflection, if I have a quantum state that is to be reflected, we're going to get an image of that quantum state at the other side of our line of reflection. So we also looked at the Hadamard operator as a reflection operator also. And this is its line of reflection. So if we start off on the 0 state and we apply the Hadamard operator, we'll end up on the plus state. And as you can see, it's an image of what we have or where we initially were about this line. And similarly for the 1 state and minus states, if we are on the 1 state and we apply the Hadamard operator, we'll end up on the minus state. So the X gate or the NOT operator is also a reflection operator. And this is the matrix for our reflection operator. So theta here is what we use to specify our line of reflection. Okay, so for quantum tomography, what we covered here was actually a situation whereby we're given multiple copies of a quantum state, or we're given multiple copies of a quantum state, and we don't know what that quantum state is. And we're supposed to use these copies to collect some data with which we're supposed to use these copies to collect some data. And we're going to use the data we collect to reconstruct the states. So to accomplish this, given our quantum states, we can measure it and calculate the number of times you get the 0 state and the 1 state. So we measure the quantum states we're handed, and we calculate the number of times to get 0 and the number of times to get 1. And from there, we have magnitude information about what the state initially was. So let's say we had 1,000 copies. If we measured all of them, if we were to get, let's say, 500 of the 0 states and 500 of the 1 states, we can say, for example, that the states were handed was in equal superposition, and it could be the plus state, for example. So we've collected some magnitude information about the states that were handed. But the magnitude information is not necessarily sufficient to describe our quantum states, because the plus state and the minus state, for example, they have the same magnitude, but there's a difference in phase between these two states. So to differentiate these two states, one thing we might do is to apply an operator before we measure. So if we are to apply the Hadamard operator before we measure, for example, the plus state will become the 0 state and the minus state will become the 1 state. And from there, we'll successfully be able to differentiate these states. So the difference between these two states, so these two states are different by some local or these two states are different by some local or relative phase. So so for these two states, because the phase difference is local, we can successfully differentiate them. But if we had the plus states and the minus plus state, for example, these two states are different by some global phase. And if we were to apply some operator before we measure, we won't successfully be able to differentiate these states. Okay. We also looked at 2 qubits. And here, we just wanted to describe a quantum system with 2 qubits. So here we have our 2 qubits are both in the 0 state, and we can describe this with a 4-dimensional vector. So to get the vector you see here, we just need to take a tensor product of the 2 individual qubits. Similarly, for the 0-1 state, we just take a tensor between the 0 state and the 1 state. And same thing for all the remaining states. Then here, we can also combine operators. So the Hadamard operator is an operator that we apply to a single qubit. But if we wanted to apply, like, if we wanted to apply two Hadamard gates to two separate qubits, we can also create an operator that accomplishes this. So we just do this by taking a tensor product, and now we have a 4x4 matrix. So with the operator you see here, we can apply two Hadamard gates to two separate qubits. So that's all that we're looking at here. We're actually checking to see if by combining the two Hadamard gates, we're going to get the same results as applying them separately. And when we tested this out, we actually got exactly the same results. Okay, then here we came across the CNOT operator. So we've already seen the CNOT operator a few times, but I'll just still explain it once more. So the CNOT operator works such that, okay, the CNOT operator is a 2-qubit operator. So we can't apply the CNOT operator to a single qubit or even 3 qubits. We apply it to 2 qubits. And it works such that one of our qubits is the control or the control qubit, and the other qubit is the target. So here, the first qubit is the control qubit, and the second qubit here is the target. So if the control qubit has a value of 0, we're going to do nothing to the target. So if the control qubit has a value of 0, the target stays the same. But if the control qubit has a value of 1, then we flip the value of the target. So 0 here becomes 1, and 1 here becomes 0. So we apply a NOT operator to the target if the control qubit has a value of 1. And this is how we make use of it in our circuits. So CX here represents our CNOT operator. And the first parameter here is the location of our control qubits. And the second parameter is the location of our target qubits. Okay. I think that's pretty much everything I wanted to review. So I think I'm going to move on to entanglement and superdense coding. But before I even start off with entanglement, let's revisit correlation. Okay. So when we looked at correlation, we had some explanation with which we utilized 2 coins. So we had a situation where we utilized 2 coins. So I'm going to describe the experiments that we spoke about. So we said Daniel's dad has 2 coins, a euro and a cent coin. And what he's going to do is that he wants to play a game with Daniel and Daniel's sister. So he's going to take the euro coin and toss the euro coin. If the euro coin lands on head, he's going to ensure that the cent coin is also facing head. And if the euro coin should land on tail, he's going to ensure that the cent coin is also facing tail. So when he does this, he's going to give 1 coin to Daniel and the other coin to Daniel's sister. So if Daniel looks at his coin and he sees that it's facing head, he'll know that his sister's coin is also facing head. And if he was to look at his coin and he sees tail, he'll also know that his sister's coin is facing tail. So to accomplish this, we utilized two operators. We utilized the fair coin toss operator, and that was how we accomplished that was how we got the state you see here. And this is our second coin. So this is the first euro coin to which we applied the fair coin toss operator. Then after that, we applied a C0 operator on the euro coin and the cent coin. So when we're done with this, this was the state we got. And we said that it's correlated because, as you can see here, half of the time, we would expect both coins to be head, and half of the time, we would expect both coins to be tail. Okay, so entanglement. So the first concept that we're going to review here is entanglement. And entanglement is an essential quantum resource for quantum computing or quantum technologies in general. So for entanglement, all entanglement is for entanglement, we have correlated quantum particles, and they affect each other instantly, regardless of the distance between them. So I'm going to use a similar experiment, but now we're going to be talking of quantum coins to describe entanglement. So same way, Daniel's dad has two coins. So he has a quantum euro coin and a quantum cent coin. So what he's going to do is that he's going to toss his quantum euro coin. And we can accomplish this by applying the Hadamard operator. Then when his quantum euro coin is in superposition, he's going to apply a C0 operator on his euro coin and his cent coin. And when he's to do this, he's going to have two coins that are spinning. So he now has two spinning coins. So he'll give one of the spinning coins to Daniel and give the other spinning coin to Daniel's sister. So if Daniel was to allow his spinning coin to land, let's say it lands on head, then Daniel's sister is to allow her spinning coin to land. It's also going to land on head. Or if Daniel's spinning coin was to land on tail, when his sister's spinning coin lands, it's also going to land on tail. So based on the definition we said we have correlated quantum particles. So as you can see here, we have two quantum particles that are correlated. And the thing is that if we were to measure one and instantly measure the other one, we're going to have correlated results. So it's almost as if they affect each other, regardless of the distance between them. So these are entangled particles. So one thing you might say is that okay, so before we knew that they affected each other instantly, one thing we would have thought of was that we would have said we have our two quantum particles or our two quantum coins. And we might say if the first coin is to land on head, for example, it can send some information to the other coin telling it that when it lands, it should also land on head. So we have our first coin, it lands on head. And if it's to do this, it can send some information to the other coin, telling it to also land on head. But the thing is that based on experiments, the results we get, the results we get, okay, based on experiments, they would have affected each other instantly, which doesn't make sense, because if they were communicating, then some time would have need to pass for, let's say, light, for example, if they were using light to communicate, some time would have to pass for the light to travel from the first coin to the other coin, or, okay, beyond even light, let's just say some waves. But based on experiments, we've seen that they affect each other instantly. So that would mean the wave was traveling faster than light, which doesn't make sense, because that would break the theory of relativity, or it won't correspond with the theory of relativity. So one other thing you might say is that maybe when the two coins were together, so when Daniel's dad had the two coins located in the same place, it's possible the two coins had discussed and told themselves, when we both land, let's both land on head, or when we both land, let's both land on tail. But a couple of experiments have been conducted. So you can take a look at CHSH. I think it was conducted by Bell. So from this, we see that these two coins don't communicate beforehand, or you don't decide on what they're going to land on before they actually do. So, okay, so that's entanglement. It just behaves in some spooky way, and lots of theories have been presented to describe entanglement, but it's just this weird behavior that you're seeing here. So, okay. We have, okay, so we're going to look at a couple of circuits that will utilize entanglement. And one of these circuits is the one that we're going to utilize for superdense coding, and the other is for quantum teleportation. So for entanglement, Einstein called this spooky action at a distance, because, yeah, it was just something that didn't make sense to what he understood at the time. Okay, so moving on to the circuit for superdense coding, what we're going to try and accomplish here is that we're going to send a single qubit. So we're going to send a single qubit, just one qubit, so one qubit. But we're going to encode 2 bits in our single qubit. So we're going to encode 2 bits in our single qubit, but the qubit here should be part of an entangled pair. So let's see how the circuit works. So we have Asja and Balbis, and they are working together in some lab, and they create an entangled pair. So this is how we create the entangled pair. So in the case of our coins, we know that the Hadamard is a fair coin source for a quantum coin. And then we have the C0 operator here, which we've used to create correlation, or which we saw which we made use of to create correlation earlier. So at this point, we have our entangled pair. Then now that I have the entangled pair, Azure can go to one location and Balvis goes to another. Then Azure wants to send two classical bits. So two classical bits to Balvis. Azure wants to send two classical bits to Balvis, and she's going to do that by sending her single qubit. So the qubit that she has to encode to include the classical information in her qubit, she's going to apply a couple of quantum operators, or she's going to decide if she'll apply a couple of quantum operators in order to encode this information. So we have two gates here, the Z gates and the X gates. So let's say Azure wanted to send the values 00 to Balvis. So we have two classical bits here, 00. So she wants to send these two classical bits to Balvis. If that were the case, she's not going to apply any of the gates you see here. So her entangled qubits, exactly the way it is, she'll send it to Balvis, and Balvis can decode the information she sent. And when he does this, he's going to receive 00. But let's say she wanted to send 01 to Balvis. So she wants to send 01 to Balvis. If that were the case, because B here is 1, she's going to apply only the X gates. So she has two gates, the Z and the X gates. And if she wants to send 01, she'll apply only the X gates. And if Balvis was to decode what she sent, it's going to get 01. Then she can also decide to send 10. And at the stage here, when the message is decoded, Balvis gets 10. So to send 10, she's going to apply only the Z gates. And finally, if she wanted to send 11, then she applies both gates, the Z gates and the X gates. And when Balvis tries to decode the information, he's going to get 11. Okay. So let's actually run a circuit where we see this in action. So I don't know if there are any questions at this point in time. Feel free to ask. Okay, so this is the setup for our circuits. So we have our two qubits, one for Azure and one for Balvis, and they are both initialized to the 0 states. And then we apply a Hadamard gate to Azure's qubits and a CNOT on the two qubits. And then finally, when Azure and Balvis are separated, or we've separated both qubits, depending on the information Azure wants to send, she can decide to apply the Z gates or the X gates or both, or none at all. And when she does this, she sends her qubit to Balvis, and this is how he decodes the information. So first of all, he applies a CNOT operator, then the Hadamard gate on Azure's qubit, and finally he can measure and retrieve the information she intended sending. So these are the four possible values that Azure might these are the four possible values that Azure can send. And we're going to test out all 4 of them. So we have our circuit here, 2 qubits and 2 classical bits. And we apply the Hadamard operator to Azure's qubit first, and then the CNOT operator to both qubits. Then when we've done this, we end up at the stage you see here. So depending on the value in the pair that Azure intended on sending, we either apply the Z gates or the X gates or both or none at all. So if the first value in the pair is a 1, we apply the Z gates. And if the second value in the pair is 1, we apply the X gates. So this is the stage whereby Azure has sent her qubit to Balvis, and he can apply a CNOT operator, and then the H or the Hadamard gate on Azure's qubit and measure. So this is the circuit drawn out. So once again, this is where we entangle both qubits. And because she wants to send 0, 0 here, so she's sending 0, 0 here, she won't apply the Z or the X gates. And this is where Balvis will decode the information. And when he measures, as you can see, every single time, he's going to measure 0, 0. So by not applying any of the gates, that's the Z and the X gates, Azure was successfully able to send the information 0, 0 to Balvis. Okay, here, the information that is to be sent is 0, 1. So because of that, Azure applies the X gates, and 0, 1 was successfully sent. So when she wants to send 1, 0, she applies the Z gates, and 1, 0 is successfully sent. And finally, for 1, 1, she applies both gates. Okay, so I have a question for the chat. So we said Azure and Balvis both have the entangled pair at this point, and they go to separate locations. And depending on the information Azure wants to send, she applies a couple of gates. Then Balvis finally decodes the information and retrieves the value she intended on sending. So what if at this point in time, when they've gone their separate ways, what if it was Balvis that wanted to send some information to Azure? Will it be possible for him to apply the send some information? It's Balvis that wants to send the information. Will it be possible for him to apply a couple of gates? Those are the Z and the X gates, in order to
Yeah, okay. I was going to interrupt Kenneth because of the apparent hiccup on the connection. Kenneth, you're back?
Yes. Am I audible?
Yes, I can hear you now.
But is my screen
not available at the moment?
Okay. Okay.
Yeah, if you can, once you're able to share your screen again, if you can backtrack a little bit.
Okay,
I think we
okay.
were like missing the connection for 1 or 2 minutes.
Okay, okay, okay. So I think where I was at was back here at the superdense coding circuit. And I was saying, we have Asha and Balvis here, and they've created the entangled pair. So at this point, they've gone their separate ways. So if Asha wanted, she could have encoded some information and sent to Balvis to decode the information. So my question is, if at this point it was Balvis that wanted to encode some information, can he apply the same encoding stage, or can he apply the same set of gates to encode some information and then send his qubit to Balvis to Asha to decode the information? So it's a yes or no question. So you can type in the chat. Will it be possible that instead of Asha being the one to encode the information and send to Balvis to decode, will it be possible for Balvis to encode the information and send his qubit to Asha to decode it? Okay, so someone is saying yes. The states are okay. The states after entanglement is symmetric. So yes. Okay, great. So nice answer. Anyone with a different perspective? Okay, so thanks, Nicholas. Okay, I think someone has a question, or I don't know if it was an accident, but I think I saw a raised hand.
Yeah, if someone raised the hand, you can write the question on the chat and I'll read it. You can.
Okay, okay. So I'll just continue, and when the person, okay, it was an accident. Okay. So I'll continue. So yeah, sure. Balvis could have been the one to apply the gates to encode some information and send to Asha to decode it. So let's even go over the states as they transition through the protocol. So when we start off, we're starting with an entangled pair. When we start off, we're starting with an entangled pair. So we're going to use the state you see here. Okay, then Asha and Balvis can go their separate ways, but this is the state we'll still have even when they go their separate ways. And at this point, Asha can decide the information she wants to send to Balvis. So let's say she wants to send 0, 1. Let's say she wants to send 0, 1 to Balvis. if that were the case, if that were the case, she's going to apply an X gate to her qubit. So if she's to apply an X gate to her qubit, so I'm going to drop the amplitudes for now. So just know that they're there, but I'm not going to be writing them to reduce what I have to write, to make life simpler for me. Okay, so here, after she has applied the X gate to her qubit, so 0 here becomes 1, and 1 here becomes 0. Then at this point, she has encoded the information she wants to send, which is 0, 1. So we said because we have a 1 here, so we have 2 lines to depict a classical channel here. So she has a classical bit here, 1, and it's the control for some quantum operator, which is the X gate. So this works like how the CNOT operator works, but its control is a classical bit, because you can see 2 lines here. Okay, so she has successfully applied an X gate to her qubit. And then she'll send her qubit to Balvis. So she sends her qubit to Balvis, and he can start decoding the information she intended on sending. So to accomplish this, he's going to apply a CNOT operator first, and then a Hadamard operator to the qubits that Asha sent to him. So, okay, so he's going to apply a CNOT operator first, and then a Hadamard gate to the qubit that Asha sent. So here, if he was to apply the CNOT operator, this is our control, and this is the target. And because for our control, we have a value of 1, we're going to flip the value of the target. So here, we're going to have 1, 1. And then here, because our control has the value of 0, we're going to do nothing to the target. So the target will stay the same. So we have 0, 1 here. So we've applied the CNOT operator at this point. And the next thing to do will be to apply the Hadamard operator to Asha's qubit, which is the first qubit. So if we are to apply the Hadamard operator to the 1 state, we're going to get the minus state. And if we are to apply the Hadamard operator to the 0 state, we're going to get the plus state. So we have the minus state after applying the Hadamard, and the plus state after applying the Hadamard. So at this point, okay, so let's rewrite this. So the minus states, so we have 0 from the minus states. We have 0 from the minus states minus 1 from the minor state. And then the 1 you see here, we can just write that out. So 1, 1. So the 0 for the minor states, that's what we have here. And the 1 from the minor states, that's what we have here. And then we have a minus sign here. Then for the plus states, we have 0 from the plus states plus 1 from the plus states. And then the 1 you see here, we can just write that here, 1, 1. So if we look closely at what's going on here, 0, 1 and 0, 1, they both have positive amplitudes. So they are going to interfere constructively. Whereas the 1, 1 state has a negative sign here and a positive sign here. So these states are going to interfere destructively. So 0, 1, 0, 1, we're going to get 0, 1. And then these cancel themselves out. So actually at this point, we're supposed to have 1 over 2. We're supposed to have 1 over 2 as the amplitude for all these states. So all these states have 1 over 2 as their amplitude. And at the end, we end up with 0, 1, which is what Balvis will measure. Okay, so I've actually said it several times, but this is a question for the chat. So let's say Asha wanted to send the classical bits 1, 1. Which gates will she apply on her qubit before sending it to Balvis? So she wants to send the classical bits 1, 1. Which gates will she apply to her qubits before sending it to Balvis? So you can write your answer in the chat. Okay, so just repeat my question one more time. So let's say Aja wants to send the information 1, 1 to Balvis. Which gates or what does she do to her qubits before sending it to Balvis? Which does she apply the X gates? Does she apply no gate at all? Does she apply the Z gate, or does she apply both before sending it to Balvis? Okay. So Nicholas is saying she applies both. Okay. Any objections here? Does anyone think she will do something different? Okay, so no objections. So yeah, if she send 1, 1, she'll apply both the Z gates and the X gates. Okay, so that's pretty much super dense coding. But honestly, I won't exactly say this is a very useful protocol because it's really easy to create and send classical bits. So if we're going to go through all this work to create an entangled pair and send a qubit just to send 2 bits, that's not overly useful or practically useful. Well, at least it shows a circuit whereby we can utilize entanglement for something. Okay, so I'm going to move on to the next notebook on quantum teleportation. Okay, so someone is asking, can I explain again how to send 1-1 in this quantum communication? Okay. So I'm going to explain this using the diagram, and I'll still explain it using the states. So here, we have Asha and Balvis, and they've created their entangled pair. And Asha wants to send, they've created an entangled pair and gone to separate locations. And Asha wants to send 1-1 to Balvis. So this is her classical message, 1-1. And because of that, she's going to apply these 2 gates. Because if you look here, we have a controlled Z gate and a controlled X gate, or a controlled NOT operator. And because we have our control having a value of 1, we're going to apply the Z gate in this case. And with a 1 here, we're going to apply the X gate. So the control is a classical bit, but the operator that we're applying is a quantum operator. So here, we're going to apply both because both of our classical bits or both of our control bits have values of 1. So when we apply these 2 gates, Asha is going to send her qubits to Balvis, and these are the gates he's going to apply to decode information. So after applying these gates, he's going to get 1-1 at the end. So for the states, when we're starting out, our states will be in this form. So we have our entangled pair. So once again, I'm not going to write the amplitudes. So just know that they're there. So we have 1/2 here and 1/2 here. Then at this point, they've gone their separate ways, and Asha wants to encode her information or her classical message. So at this point, she's going to apply, because the information she wants to send is 1-1. She wants to send 1-1, so she's going to apply both gates. So she's going to start off with applying the Z gates. So she'll apply the Z gates, and this is the state she's going to get. Because we have a 1 here, and if we are to apply a Z gate to the 1 state, we're going to get the -1 state. So that's why we have a negative sign here. Then she now applies the X gate. So when she applies the X gate, 0 here become 1. And 1 here will become 0. Okay, so this is what she gets after she has applied the Z gate and the X gate to encode her information. Then she sends her qubit to Balvis. So Balvis now has the entangled pair. Okay, no, is this an entangled? yeah. Or, okay, so Babis now has the quantum state you see here. And he's now going to start decoding the information. So he's going to start off by applying the sinus operator. So we have a control of 1, and our target is 0. So we're going to get 1, 1 when we apply the sinus operator to the state you see here. And then for the other side, we're going to apply a sinus operator once more. But because our control is 0, we're going to do nothing to the target. So here, we're going to have 0, 1. We're going to have 0, 1. So at this point, he now applies the Hadamard operator. So when he applies the Hadamard operator, the 1 state here will become the minus state. So we have minus and 1. And then the 0 state here will become the plus state. So we have plus and 1. So we're just going to rewrite the state you see here. We'll just rewrite this. So minus here, first of all, the minus state here consists of 0 minus 1. So we're going to write 0 minus 1. And then the 1 you see here, we're going to write 1, 1. And then, okay, so we have a minus sign here. So the plus state here consists of 0, 0, 0 plus 1. So the plus state here consists of 0 plus 1. But because we have a negative sign here, we're going to distribute it. So we now have a 1 here. So the plus state here has 0 and 1. And finally, we can write 1, 1. Okay. So at this point, a couple of states will interfere constructively while others will interfere destructively. And if you look here, we have 0, 1 and minus 0, 1. So these will cancel out. So these will interfere destructively. Whereas you have minus 1, 1 and minus 1, 1 here. So these interfere constructively. And we end up with 1, 1 at the end. So as I said, I wasn't writing the amplitude, but at this point, it's going to be 1 over 2. So when we add these and we have 2, we'll divide by 2 and we'll end up with minus 1, 1. But because this is, well, we end up with minus 1, 1. But if we're to measure it, we'll get 1, 1, which is the information that Asja wanted to send. Okay, yeah, thanks. So we can move on to the next notebook now. Okay, so here we're going to look at quantum teleportation. So for those of us that like watching sci-fi movies, we've definitely come across teleportation, whereby an object is instantly moved from one location to another. So in quantum teleportation, we're actually going to instantly move quantum information from one state to another. But there's some caveats there, which we're going to take a look at. So I don't know if I don't want you guys, I don't want like, okay, let me explain the protocol first, and I'll ask this question at the end. So this is how the quantum teleportation protocol works. So we have Asha and Balvis once more. And they are both together in some lab. So they are both together in some lab, and they create an entangled pair. Then they go to separate locations. So at that point, okay, so they create an entangled pair and they go to separate locations. So Aja is with one of the qubits in the pair and Balvis is with the other qubit in the pair. So let's say at that point, Aja wants to send some quantum states to Balvis. So let's say at that point, Aja wants to send some quantum state to Balvis. She can use the quantum teleportation protocol to achieve this. So let's look for the circuits. Let's look for the circuits that achieves this. Okay. So here we have a circuit for quantum teleportation. So this is where they create the entangled pair and they can go to separate locations. So they have an entangled pair at this point and they can go to separate locations. And with RY, Aja can pick a quantum state that she wants to send to Balvis. So when she does this, with the quantum state she wants to send and her half of the entangled pair, she can apply a couple of gates. So she can apply a couple of gates. Those are the gates you see here. And then she can measure her 2 qubits. And when she does this, she can send those classical bits she gets when she measures them to Balvis. And depending on the values that she measured, Balvis can apply a couple of gates. And when he does this, the quantum state that Aja initially intended on sending. So let's, we have a quantum state psi that Aja wanted to send. When Balvis has applied a couple of gates, he's going to have that state. Okay, so this is where the caveat is. During the course of the protocol, Aja had to send some classical bits to Balvis. So the quantum communication protocol does not happen instantly because we still have to send some classical information through a wire or with waves or something like that. But at the end, Balvis will end up getting the states that Asha intended on sending. So the quantum teleportation protocol is kind of the inverse of what we're doing with superdense coding. In superdense coding, we sent a qubit and we were able to retrieve 2 classical bits from the qubits we sent. But here we're sending 2 classical bits, and from there we're going to retrieve a single qubit. Okay. And in this case, I actually feel that this is a useful circuit as, again, superdense coding, because someone might say for the quantum state you wanted to send, she could have just measured it a couple of times and she just measured it a couple of times and send some values for A and B, for example. But if she was to do this, she might end up like with just an approximation of what the initial state that she has was. But with the quantum teleportation protocol, she ends up sending the exact state that she had. Okay, so let's look at how the states change during the protocol. So first of all, when we start off, we have an entangled pair. So when we're starting off, we have an entangled pair, which is shared between Asha and Balvis. So we have an entangled pair. Okay, then they can go their separate ways. And at that point, Asha is going to create some quantum states, which we called psi. So I'm just going to rewrite psi in this form. So we have psi such that the 0 state has an amplitude A and the 1 state has an amplitude B. So this is our value of psi that this is our value of psi, we've written psi in this form. So our quantum state psi, that's what we have here. So we have a single qubit here and we have 2 qubits here, but we can just have a combined system of all 3 qubits. So if we take a look at this, this is what we get if we are to combine these. So we have 0 multiplied by 0, 0. So we have 0, 0, 0. 0 multiplied by 1, 1. So we have 0, 1, 1. Then 1 multiplied by 0, 0. We have 1, 0, 0. And finally, 1 multiplied by 1, 1. We have 1, 1, 1. Okay, so this is what we have when we've prepared the state that is to be teleported and we have the entangled pair. So at this point, the next step is to apply a CNOT operator. So we've achieved this. We've achieved this. we've used Ry to create psi, and we have our entangle pair. Now we need to apply a C0 operator between Asja's 2 qubits and then H on the qubit containing psi. So apply a C0 operator, then H. So here, we're supposed to apply a C0 operator to the state you see here. So the C0 is applied on the first 2 qubits. So 0, 0 will remain 0, 0 because the control is 0. 0, 1 will also remain 0, 1 because the control is 0. But 1, 0 here, because the control is 1, it will become 1, 1. And 1, 1 here, because the control is 1, we're going to get 1, 0. Then we can move on to applying the Hadamard operator. Okay, so once apply the Hadamard operator to the first qubit. And this is where we do that. So this is where we do that. So for the first qubit that we're applying the Hadamard gate to, 0 become plus. So if we are to apply the Hadamard operator to 0 here, it's going to become plus, and that will give us 0 plus 1. And then 0 here, we also have the plus states. So we have 0 plus 1. Then here we have the Hadamard gate being applied to the 1 state. So we have the minus state. So we have 0 minus 1. So we have 0, the minus sign, and 1 here. And then finally here also, we're applying the Hadamard gate to 1. So we have 0 minus 1. So this is what we get after we've applied the Hadamard operator to the state you see here. So we've applied the 2 operators we intended. We've applied 2 operators we wanted to apply. So at this point, we can just rearrange the states. So 0, 0, 0 here, and 0, 1, 1. We bring those together, and 0, 1, 1 here, and 1, 0, 1. Okay, 0, 1, 1 here, and 0, 1, 0. We bring those together, 1, 0, 0, and 1, 0, 1. We bring those together here, and 1, 1, 1, and 1, 1, 0. We bring those together here. So we just rearranged the states. Then at this point, we want to measure the first 2 qubits. So we want to measure the first 2 qubits. So for these 2 states you see here, we can factor these out. So we have 0, 0, and 0, 0 here. So we factor it out. Here we also have 0, 1, and 0, 1. So we factor it out. 1, 0, 1, 0. We also factor it out, and 1, 1, 1, 1. We factor it out. So when we measure, and we measure, and let's say we get 0, 0 when we measure. Because of that, we know that the states that Balbis has. So here when we factored this, when we factored 0, 0, and 0, 0 here, these are the qubits with Asja. So the first 2 qubits are the qubits with Azure. So when we factor 0, 0, this is what we had left for Balvis. So this is now the state with Balvis. So if Azure was to measure 0, 0, then we know that the state with Balvis is the state you see here. And if Azure was to measure 0, 1, then we know that the state with Balvis is the state you see here. If she's to measure 1, 0, then we know that the state with Balvis is the state you see here. And finally, if she measures 1, 1, we know that the state with Balvis is the state you see here. So the state she initially intended on sending is AB. And if she measures and she sees 0, 0, then she knows that Balvis has AB. And we're done with the teleportation protocol. But let's say she measures and she sees she has 0, 1. That would mean the state with Balvis is in this form. And she has to send the information 0, 1 to tell Balvis to correct the qubits he has. So we should apply an X gate to the qubits he has to get what she initially intended on sending. If Balvis had the state A minus B, that is when she measured, she got 1, 0. Then she'll send 1, 0 to Balvis and tell him to apply a Z gate to the states he has so that he successfully has AB. And finally, if he has minus B A, she'll send 1, 1 to him, telling him to apply an X gate and a Z gate so that he successfully has what she intended on sending. So if you look at our circuit once more, that's why she's sending classical information. It's to tell Balvis the gate to apply to correct the qubit that was successfully teleported to him. So in our quantum teleportation protocol, A and B were successfully teleported to Balvis, but he still needs to apply some gates to like correct the states that was sent to him. So I don't know if this protocol was clear or if there are any questions. So in the quantum teleportation protocol, we were successfully able to teleport A and B to Balvis. The only problem is that they didn't arrive in the exact form she intended on sending them. And he needed to apply a couple of operators to correct the states. Okay, so if there are no questions, I have a question. So what do you think? With quantum teleportation, do you think we'll ever be able to teleport classical objects like, let's say, a human being, for example, or even a car or something like that? So you can type in the chat, like, what do you think? I'm just thinking back to some Star Trek movie I watched a couple of years back where I think Captain Kirk was riding a bike and they were teleporting him with his bike. Okay, so it looks like no one has an answer to this. So in the meantime, we can actually teleport quantum information, and we'll just have to wait and see if we're able to teleport classical objects in the future. So, so we have just 2 more notebooks, multiple control constructions and phase kickback. So I said I'll cover phase kickback today, so I'll start off with that. Okay, so here, we briefly described phase kickback yesterday, and we said in phase kickback, we want to apply a controlled operator. Let's say the control not operator, for example. And when we do this, it's the control qubit that is affected, not the target. So with phase kickback here, we have an interesting quantum effect whereby we apply the control not operator and the control qubit gets affected instead of the target. So let's see how to accomplish this. So this is a circuit we can actually use to do that. This is a circuit we can actually use to do that. So this is the initial state of our qubits. Okay, this is the initial state of our qubits. And then we apply Hadamard gates to both qubits. Then we apply a CNOT operator where this is our control and this is our target. Obviously, we've applied Hadamard gates to the states you see here, but the first qubit is our control and the second qubit is our target. And then we apply Hadamard gates once more, and then we measure. So let's see what happens in our circuits when we do this. So we have our quantum register here with 2 qubits and our classical register with 2 bits, and we introduce them to our quantum circuit. So we apply an X gate to the qubits at location 0 because we want to have the state 0, 1. Then we move on to applying Hadamard gates to both of our qubits. And then we apply a CNOT operator where the qubit at location 1 is our control and the qubit at location 0 is our target. Then we apply Hadamard gates or operators once more, then we measure. So if we are to do this, let's see what we get at the end when we measure and retrieve the count. Okay, so this is our circuit. So when we initialize our circuits, we obviously start off with 0, 0. But because 1, 0, 1, we'll apply an X gate here, and then we have 0, 1. At this point, we apply H gates, and we have the plus state here and the minus state here. Then we apply a control not operator and a couple of Hadamard gates. And when we are to do this, we end up with 1, 1. So if we look closely, we had 0, 1 at this point, and we applied a couple of gates where a controlled NOT operator was included. And at the end, we have 1, 1. So in fact, actually what happens here is that when we apply the controlled NOT operator, we end up with minus minus here. And then when we apply HH, we get 1, 1. So here, it's our control that changed from the plus state to the minus state, whereas the target stayed the same when we apply the C0 operator. So at the end, we've successfully measured 1, 1. And this happened every single time when we set shots to 1,000. So the circuit was run 1,000 times, and every single time we ended up with 1, 1. Okay. Okay, so let's look at how this actually happens in more detail. So let me check if I have any questions in the chat. Okay, so I'm seeing, do all the states start being 0? That's why if you want to define it to be 1, you have to apply a NOT. Okay. The question was just answered. Okay, so thanks for whoever answered that. But yes, when we start off, our states are in the 0 states, and when we start off, our qubits will all be in the 0 state. And then to get 0, 1, we applied an X gate. Okay, so here.
Hi, Kenneth.
Yes.
There's just one extra question in the chat that just came out. Do you want to read it, or should I read it to you?
Sure, you can read it.
So this is from Cairo Hiki. Quote unquote, he asks, so this acts as a 1 gate? I imagine he's referring to something you said previously. A 1 with as a constant gate, I imagine.
Okay. No. This doesn't, it doesn't act as a 1 gate. Okay, so I don't know the gates you're even referring to that acts as a 1 gate. But okay, so we have our circuits and we request for a couple of qubits. So I'm going to draw, okay, in this case, since we're requesting for 2 qubits, I'll draw 2 storage locations here to represent our 2 qubits. So when we're starting off, we just have our qubits starting off with 0 here. So all our qubits start off with 0. But for the phase kickback implementation that I wanted to view here, we wanted 0, 1. That was why we applied an X gate here to convert 0 here to 1. So we applied an X gate to this qubit, and the 0 became 1. So we now have 0, 1. So gates like the constant 0 or constant 1 operators, those operators aren't even reversible to begin with. So we don't even utilize them in our quantum circuits. Okay, so I think there's more explanation concerning that question. I said this because state 0, 1 turned to 1, 1. Oh, okay. State 0, 1. Okay, so I don't know exactly where the confusion is coming from. Let me explain this once more, and hopefully it will clarify things. So when we start off, all our qubits will begin with 0. All our qubits will begin with 0. And then we were looking for a 0, 1. That was why we applied an X gate here. So this makes it 0, 1. But let's imagine when we initialize our qubits, this is not the case, but let's imagine they all started off with a 1 state. If we were to apply an X gate here, we're going to get 1, 0. So this is not a constant operator, because for a constant operator, regardless of what you start off with, you're always going to end up with something. So for a constant operator, let's say we were dealing with the constant 1 operator. Okay, let me write 1 in numeric form. Let's say we're dealing with a constant 1 operator. If we initialize our qubits to 0, because of that, we're going to end up with 0, 1 here. But let's say they started off with 1, 1. In that case, if I had a constant 1 operator, we're going to have 1, 1. So it's not the same. This is still an X operator. We were interested in getting 1, so we applied X to 0. Okay, let me just return everything back to what it was. So we were interested in getting a 1 here. So we applied X to 0, and it made it 1. It's not the same as applying a 1 operator. And as I've said, 1 operators aren't even reversible to begin with. So we're never going to use something like that in our quantum circuit. Then at the other part, I think it's concerning something going on here. So let's write all the states to see how they transition. Okay, sorry, this is 0, 0. Okay, so at this point, we'll have 0, 1. When we apply the H gates here, we're going to get plus and minus. Then here, we're going to get minus, minus, then 1, 1. So also here, there is no operator here that is a constant operator, because the Hadamard, for example, as you can see, if you apply to 0, we get plus, and if you apply to 1, we're going to get minus. And now we have the C0 operator. So for the C0 operator, here, we had minus and it stayed the same. Okay, actually discussing the C0 operator with the plus state and minus states, it's kind of tricky, but okay, let's say we're dealing with C0 where our control is 0 and our target is 0, for example. So here, okay, it will still stay 0, 0. But if Here we have a 1. The output will be 1. So as you can see, it's not a constant operator at this point. Even here, so like nowhere, like there's nowhere on the C0 operator that will have a constant operator. The way it works is such that, like up here, it's almost as if we have like an identity. And below, we either have an identity or a not operator, depending on what the value up here is. So there's no constant operator anywhere. But for what's going on here with phase kickback, that is what I was about to like move on to explaining. Because you know the plus state here consists of 0 and 1. Even the minus state consists of 0 and 1. So we're going to see why this happened soon, or that's the next thing I'm about to like look at. Okay, so let's move on. Here, okay, so let's look at the effects of phase kickback more closely. So we had the 0 state and we applied H and we got the plus state. We also had the 1 state and we applied H, then we got the minus state. So we have the plus state and the minus state. Okay, so now we can multiply. So we have a tensor, but we'll just do this the same way we do normal multiplication. So we'll distribute 0 and 1. So here, the 0 we have here, that's what we have here. And 1 here, that's what we have here. Then everything, the minus states we have here, here and here also. So same way we do normal multiplication. And at this point, we get to apply the C0 operator. So if we were to do that, because we have 0 as the control, we're applying an identity to the minus state, so nothing happens. So as you can see below, the minus state stays exactly the same when we applied C0 here. The minus state stayed exactly the same. But here, because we have 1 as a control, we're meant to apply a not operator to the minus state. So if we apply a not operator here, 0 when we apply not will become 1, and 1 when we apply not will become 0. So 0 here becomes 1, and 1 becomes 0. So we have 1 minus 0 here, but let's say we were to factor out the negative sign, or we were to factor out minus 1. We get 0 minus 1. So this and this are exactly the same. And that's exactly what we do here. So we just factored out the negative sign. So we now have 0 minus 1 with a negative sign at this point. And because we tried to multiply here, and we distributed the minus state, we just return back to the form you see here. So from this form, we'll just head back in the opposite direction to the form you see here. So from here, we'll just bring the zero states and the one state together. So that's how we end up with this. So the 0 here, that's how we have 0 here. And the 1 here, that's how we have 1 here. And then our minus states, still the same minus state here. So now at this point, we can apply the Hadamard operator once more. And if we apply the Hadamard operator to the minus state, we're going to get the 1 state. Similarly here, we apply the Hadamard to this, and we get the 1 state. So that's what happens in phase kickback. We had the plus states. So we had we had the plus state and the minus state here. We had plus minus. And then when we applied C0, we ended up with minus minus. So, okay, no, not here. We ended up with we had plus minus, but when we applied the C0 operator, we ended up with minus minus. So if you look at our circuit, we had the plus minus states, but when we applied C0, a negative sign got kicked back here. So this is where phase kickback actually occurs, and we get minus minus. Okay, so I'm just going to jump on to the final notebook on multiple control constructions. And we can call it a day. Okay, so we spoke of the case whereby for the C0 operator, if the control is 1, then we apply a not operator to the target. But what if we wanted a case whereby if the control was 0, that's when we apply a not operator to the target. So that's the operator that is being described here. If the control is 0, then we apply a not operator to the target. So to do that, we can just utilize X gates in our circuits. So in the circuit you see here, we have 0, 0. And then because we applied an X gate here, we end up with 1, 1, 0. And we have a 1 here, so it will trigger the C0, and we end up with 1, 1. Then here, we just return this back to what it originally was. And now we have 0, 1. So we have a case whereby 0 is our control, and 0 stays the same at the end. But 0 triggers the C0, and 0 here now becomes 1. So we applied a C0 even though, or when the control was initially 0. So thus far, we've been looking at just the C0 operator. So the C0 operator has a single control, but we have another gate here, the C0 operator, or the Toffoli gate. So it utilizes 2 control qubits. And here, it's when both qubits are 1. So when both of our control qubits are 1, then we apply a not operator to the target. And we have some variations of this here. So here, when both of our controls are 0, then we apply the not. When we have 0, 1, we apply the not, or when we have 1, 0, we apply the not operator. So to accomplish this, we'll just utilize X gates for both of our qubits. Here, we'll utilize an X gate for the first, and here we'll utilize an X gate for the second qubit. And even beyond the Toffoli gates or CC knots, we can have CCC knots, or even as many controls as we want with the MCT gates. So for CCC knots, we can actually create this by utilizing the Toffoli gates or CC knots. And this is how we do this. So here we have, so these are the control qubits. So we have control, targets. And we've introduced an auxiliary qubit. So we've introduced an extra qubit here to create CCC knots just by using the Toffoli gates. So this is how we do this. If we have 1, 1 here, this will become 1. And then now we have a 1 here and also a 1 here. So because we have 1, 1, we will trigger this and it will become 1. And then finally, we can use this to return the auxiliary to what it was. So 1, 1 here, and it will return this to 0. So this is just to return the auxiliary to 0. But when we have 1, 1, 1, we're successfully going to be able to trigger the C0 operator, or the CCC not operator, which is what this is actually. But when we have all ones for our controls, then we actually apply a not operator to the target. And okay. So here we even have variations. So we have 4 controls and the not operator. So as you can see, for this, it's when we have 1, 0, 1, 0. That's we apply a not operator to the target. So this will become 1, 1, 1, 1. And we're even utilizing 2 auxiliary qubits here to accomplish this. Okay, so that's pretty much everything that we have to cover for today. So there are a couple of tasks here that you can take a look at in your own spare time. So one thing I want to point out about phase kickback is that, so for phase kickback, so for the circuit you see here, so let's say we had an X operator here, an X gate here. So in that case, okay, so we have 0, 1. Sorry, we have 0, 1 here, and at this point we have 1 and the minus state. So because 1 is going to trigger the C0 operator here, 1 is going to become -1. So 1 will receive a negative sign. So that's how phase kickback works. Anything that is going to trigger the control not operator will receive a negative sign. So, okay, let me even So let's say in our multiple control constructions notebook. Okay, so for example here, let's say we had the minor state here. So we had the minor state here. And we know that 1, 0, 1, 0 is what is going to trigger the C not operator. So we know that this is the input that we're going to apply to trigger the operator. So in that case, it is 1, 0, 1, 0 that will receive a negative sign, because it is what is going to make us apply a not operator to the target. So I think that's pretty much everything I have on my end. I don't know if there are any questions at this point in time. I guess time is actually up. So we can call it a day and move on to the talk.
All right. Thank you, Kenneth. Do you want to stop the recording yourself, or should I do it?